we start Module 3, Recursive Algorithms. Part A, Introduction to Recursive Algorithms. The first video, 8.1, First View of Recursive Algorithms. I think you have heard recursive algorithms. But in this module, we want to really understand this very important algorithms, completely. So we will use several examples. Then from the theoretical side, then, work on some concrete examples. Then we should have pretty good understanding. All right, so let's start. The first question. Why recursive thinking is important in problem solving. Here we can see to solve a problem, there is a special thinking way. So that is different from most people frequently used. Because most people, so they tend to use straightforward thinking, right? So step by step. So that's the typical way. But recursive way is quite different. Recursive way has some big difference if we compare with usual thinking. So let us understand this question first. So we're used to straightforward, non-recursive thinking in problem solving. All right. But we noticed some problems can be solved in both ways, non-recursive way and recursive way. And we like to compare them. Advantage, disadvantage. Non-recursive way has its own advantages and disadvantages. Recursive way has its advantages and disadvantages. So we will compare, the main advantages, disadvantages part. All right, so another important part, why recursive thinking is important. Power of recursion. It is powerful. It is very powerful. So we will, try to feel about it, feel the power of recursion. Some relatively hard problems. So here you can see when we try to use the power of recursion, usually we work on relatively hard problems, relatively. Because hard or easy, it is subjective, right? So here I said relatively hard. But in another view, you can see if the problem is pretty easy, then we do not need to use recursion. Although you can use recursion, but you may not get a good result. But for relatively hard problems, then recursion method is more and more important. All right. So we will see that point quickly. All right. So here, another thing I want to point out is some relatively hard problem can only be solved by but I put it in a parenthesis. Because some people may argue about it. Because based on our textbook, the author thinks any problem that can be solved by recursion can also be solved by the non-recursion method. But in the real world situation, that could be really, really hard. Really, really hard. Our second example, you will see it is extremely hard if you want to solve it without using recursion. So for that reason, I put this parenthesis. Yeah. All right. Now let us compare advantages, disadvantages a little bit here. Yeah. First, non-recursive method we call the iterative method. So we do it by iterations without recursion. Yeah. All right. So then recursive method. Yeah. All right. Advantage, less resource. Less resource. Comparing with recursive method, less resource. Yeah. But why? It is a pretty long story. Yeah. I will talk about that. Harder implementation. Harder means for relatively hard problems. For relatively easy problems, not hard. Yeah. So for relatively hard problems, harder implementation. All right. Yeah. Then recursive method, more resource. Yeah. Easier implementation for those relatively hard problems. All right. Yeah. But here, the biggest question is why iterative method use less resource? Why recursive method use more resource? Because the answer, I need to use at least 5 minutes to explain. Yeah. So I leave that explanation to, in our comprehension questions. Then I have one question related to this comparison. Yeah, I will explain at that time. Yeah. So for this video, I just save a few minutes. Yeah. But we delay it. Yeah. We will, here I can point out one important concept. Recursion implementation using stack. Stack data structure, right? Yeah. Inside memory using stack data structure to implement recursion. Yeah. The stack implementation requires resource, right? Yeah. Iterative, we do not use stack data structure to implement. The stack implementation uses relatively more resource. Yeah. All right, so later when we go there, I will draw a diagram to show you the idea. Yeah. All right, so let us look at our first example, question number 7. Calculate the factorial. It is a simple question. Very trivial, but in order to understand, compare recursive, iterative, yeah. So let us start from this very simple example. Yeah. The question part, given a non-negative integer n, yeah. Find its factorial. N exclamation sign. Yeah. You know the meaning of factorial. Yeah. The method 1, iterative method. Yeah. Based on its definition, we can write n factorial as a product of n consecutive numbers from 1 through n. Yeah. Yeah. All right. Yeah. But here there is one base case. N when n equals 0. Yeah. Because here we said non-negative integer, right? 0 included. Yeah. 0 included. N greater or equal to 0. So, but when n equals 0, what is 0 factorial? Right? Some people, if you just use your intuition, it is very likely people may say 0, right? 0 factorial equals 0. Yeah. But actually, it equals 1, not 0. Can you understand why it equals 1? Does it make sense? Yeah. So because here, by intuition, how do you imagine? How do you, based on this kind of definition, you can understand it equals 1. It is not easy, right? Yeah. But we need to find a, reasonable way to explain it. Yeah. So we will justify it in our next slide. Yeah. All right. Then the implementation of this method, very easy. Yeah. 1 for loop. Yeah. Everyone can do it easily. All right. Now let us move to method number 2, recursive method. Now, here, although it is an extremely easy question, but we like to go through the recursive procedure to help us understand the basic elements of recursion. Yeah. All right. The main idea for recursion, yeah, it is a general problem-solving approach. Yeah. So what's that? I think all of you have heard of that. Divide and conquer approach. Divide and conquer. Yeah. So I think you understand the meaning, right? Yeah. This is a big thinking method for our algorithms. Problem-solving method. Yeah. Big one. Yeah. And here we start using it in this module, but our module 4, we will completely use module 4 to discuss divide and conquer. Yeah. So we need to spend much more time studying divide and conquer approach. Yeah. All right. Next, let us look at the solution of method number 2, recursion way. Yeah. All right. First, let me give you 3 properties for the recursive method. Yeah, the first one, the problem is easier when the size is smaller. Yeah, that's true. The problem size relatively small, or we start from the very beginning, the size very small, then the problem very easy. Yeah. After that, so then when we work on a problem of current size, because the size can change, yeah, or we increase the size one by one, and when we look at the question of the current size, so there is a number there. Yeah. Assume that the problem of a smaller size has been solved. Now, when we work on the current size, we can assume the problem with a smaller size has already been solved. Why? Because we go through, from there, right? So we increase the problem size, sometimes one by one, but sometimes we can increase by certain number, not necessarily one, certain number. Okay, yeah. The third property, then there is a gap, right? Yeah, there is a gap. The problem of current size, the problem of previous size, between these two sizes, there must be some gap. We need to fill that gap. So fix the gap through a recurrence relation. So we need to derive that recurrence relation. And this step is critical. To solve a recursion problem, this is the most important step, the critical step. After you have the recurrence relation, then most people can solve it easily. Yeah. All right. So for our factorial problem, let us derive that recurrence relation first. Yeah. First, we define a function f of n as the factorial function. Yeah. After that, we use the, problem size reduction. Yeah, here, so there is a, new concept. Problem size reduction. Yeah. How do we do reduction? Yeah, there are many different ways you can do, but the simplest one size reduction. Reduce the size just by one size reduction. Okay? Here we chop off the last operand in the product. Yeah. So the problem size reduced by 1 before that line. Yeah. So the problem becomes, if we still use the f function, f of n minus 1. Okay? Yeah. Then fill the gap, right? Yeah. Fix the gap using recurrence relation to bridge the gap. Okay? So we can get the recurrence relation easily. F of n equals f of n minus 1 times n for n greater or equal to 0. Yeah. In this factorial definition, because it is hard to imagine when n equals 0, right? Yeah, hard to imagine. It becomes 0, right? In order to make this product make sense, yeah, here we assume n greater than 0. Here you can see we exclude the 0. So here the question, when we derive this recurrence relation, we need this condition. Yeah. So that's slightly different from our original problem. Our original problem, there is no recurrence relation, right? Yeah. So we discover this recurrence relation. After we discover it, in order to make this recurrence relation makes sense, right? Makes sense. Yeah. We need this condition. Okay, so no conflict. Yeah. All right, so let us continue. Yeah. At this point, we are ready to understand why 0 factorial equals 1. We can justify it. Yeah. How to justify? Very simple. Yeah. We use this recurrence relation. We use it. All right. Then we do formula transformation in this way. Yeah. F, we do equivalence transformation. Equivalent transformation. So f of n minus 1 equals f of n over n, right? So we divided both sides of the recurrence relation by n. So we get this equivalent equation. Equivalent. All right. After we get it, can we set n equals 1, right? Because n equals 1, still n greater than 0. Yeah, so it is legal, so we can set n equals 1. We do not set n equals 0, right? If n equals 0, it is illegal. Yeah, you look at that, this fraction, it is illegal, right? So we cannot set n equals 0, but we can set n equals 1. After that, look at both sides of the new equivalence equation. F of 0 equals f of 1 over 1. We know f of 1 equals 1, right? 1 factorial equals 1. That's trivial. 1 over 1 equals 1. Can you connect this result back to 0 factorial equals 1? Because f of 0, this is 0 factorial, right? By definition of the function. Think about it. By definition of the function. But you may argue, some student, so you may argue, when we define f function, we do not allow n equals 0, right? Yeah. That's possibly true, even if you do not allow it. But after, because we know this equation is correct, right? After we see this equation, we can extend the definition. Can we extend the definition to cover 0? Yes. Based on this result, we can do extension. We can do extension. In math, many times we can do things like this. When we do our first definition, we may not cover everything. So we only cover things that we feel it is correct. But after we derive some new relations, then we can extend our definition to cover more cases. So in math, so this idea is used many times. Yeah. All right. Yeah. So the reference for this part, so you can find from our textbook, chapter 4, page 131. Yeah. All right, so the conclusion after we did the first simple example, at least we get this conclusion. It is an interesting way to solve problems. Yeah, so interesting, new way, But our next video, we want to see the power of this method. Not just interesting, it is very powerful. All right, so let us stop right here.